concurrency. All right. So previously on Suite 212, I talked about threads. I went down, covered the basics of threads, and covered the reason why people like threads, and the pitfalls and the problems that threads bring. And just so a little short summary. Threads are great to model activities that are naturally concurrent in the real world. So when you have to interact with the outside world, and those interactions are naturally concurrent, then modeling that with threads inside your program is a very natural mapping also. And another reason for using threads is because it's a relatively simple model for running things in parallel, if your hardware so allows. But there's a lot of problems, as I said. It can make programs very confusing, and the reason is that now that the threads share the heap, basically the state of the application, the objects can be shared between the threads. Then now bad things can happen, things that don't happen in single thread programs. In particular, race conditions can happen, and they are very hard to reproduce. Then you have to start adding locks for certain blocks of code. But then you get into the other problem that maybe you lock too much and you may end up with deadlocks, and the locks themselves are heavy duty in terms of performance, so your program can perform worse. So there's all sorts of problems with threads. So they are cute and furry beasts, but they are beasts. So don't be deceived by how simple it is to create them, because it's much harder to control them. So they basically, you can use threads, but they might be restrained. You have to use threads with a lot of care, basically. Okay, whenever you bring threads into your program, into your software, you better have a very clear model of how those threads are going to be used. Basically, you have to have what's called a thread model, some sort of a higher level architecture for what exactly in your program is using threads and how. Okay, what gets shared, what doesn't get shared, and depending on the language, those thread models may be given to you by the language, or you have to add this layer of conventions and self constraints of how you write the code, in order to be able to achieve that model of concurrency that you think that you need. All right, so I'm going to talk about three concurrency models that are very well known, and they are sort of Swiss knives in many ways of concurrency. They are thought for different scenarios of concurrency. They don't compete with each other, so they are for different kinds of applications. But it's good to have those three basic ideas in mind when you recognize that you have some sort of a concurrent situation in your hands. So the first one is actors, which is an exercise that I know that some of you are already tackling. And actors is a model that is good for independent tasks. Basically, it's when you have a situation where the different parts of your program are actually doing completely different things concurrently. So that one part of your program maybe is handling, input from the user. Another part of your program is doing, I don't know, so listening for messages on the network or something like that. So when things are doing when the concurrent parts are doing completely different things, then actors is a relatively good way of thinking of the concurrency model that you may want to add. And I'll go a little bit deeper on each one of them. tuple spaces are, or data spaces is a concurrency model that is appropriate when you have a situation where you have a part of your program that is producing data and a part of your program that is consuming that data. All right, and so when you get into those kinds of situations, so I don't know, for example, it could be one part of your program that is reading data from somewhere, from files or from the network or something. And then you have another part of your program that's actually doing the processing, right? So in that case, the tuple spaces is an interesting model where you have a shared space of data where you basically have producers, consumers. The producers put the data in the shared space and the consumers take the data from the shared space. And there's a very clear definition and separation between producers of that data and consumers of that data, right? There's like, you produce, you put it there, and that's all you do. And if you're a consumer, you take the data out. You actually take it out of that data space and you process it. Okay, so that's a model for those kinds of situations. And finally, a third one is called MapReduce. Was popularized by Google a few years ago, but it's actually not. It was not invented at Google. It comes from much further in the past. It actually was already in Lisp in the 1960s. So MapReduce, and I'll talk a little bit more, is there are actually many aspects to MapReduce, okay? And I will talk this week about one aspect, which is the concurrency aspect of MapReduce, and how to, how to do these kinds of data-intensive parallelizable situations when you have, but the other aspect of MapReduce, I'll talk about it next week, which is the aspect of streams, of having data streams and data that flows through your system. And there's a source and there's a sink. And so MapReduce is a combination of a concurrency model and a sort of a streaming, also a data model that is a streaming data. But this week I'll talk more about it's a model of concurrency. But basically, it's good for data-intensive parallelizable situations. When you have a task at hand that can greatly be accelerated by having a lot of workers doing the same thing, right? And then it's also a situation where at some point you still need to produce one result, right? It's not like you don't necessarily stop when you have the final data all separated, right? What you need, that you still need to kind of converge that separate intermediate data. You still have to process them and merge them somehow. That's the part of the reduction of the data. But basically, it's good for data-intensive parallelizable. So these are all different situations, and the models that they have. That's where they shine, is when you have those situations, and then you may think of these models that you hear here in this class. So let me dive a little bit inside each of these models. So the actor model, it's essentially the letterbox style in chapter, 12, not 11, 12. This is from my previous version of the book. So this is one of the exercises that you did a couple of weeks ago. And so it's basically that model, but with threads. So the idea is that there are actors in your software, and these actors are typically associated with concept of an object, right? But now these actors, what will make them actors is that each of these actor objects have their own thread. Okay, so each one has their own thread. So if you have many things, in your program that are doing separate things and different things, and you have actors of different types, right? But each one has its own thread, and each one of these actors is doing essentially what the letterbox style did in chapter 12, which is listening for messages and reacting to the messages that are coming. So actors send messages to each other, but then the message processing is concurrent, right? So now there's concurrency in the system. It's not just one single thread like in chapter 12. Each actor has its own thread. But the important thing, and this is where, you know, there's a fine line, there's a clear distinction between languages that support the actor model by default and languages that don't. And one famous one that supports the actor model is Erlang. Some of you may have heard. So Erlang is a language that has been designed with the, you know, around the actor model. It's a relatively old language. It became popular relatively recently, but the language is old. It's like 30 years old or something like that. So it's not a very recent language, but it was designed around the actor model. This idea that you have concurrent objects, and they don't share data. They don't share the data. Okay, that's an important thing. What they do is that they send messages to each other, and what that means in Erlang, so in the true actor model, is that there's actually, it's as if they were in separate machines. So if you send a message to another object, if this object sends a message to another object, the data does not go by reference, it goes by copy. So there's a separate, you know, a duplicate, a copy of the data gets sent into the actor model. So there's no data sharing, right? Basically, there's no data sharing among the actors. And so once you have that, you avoid shared memory. And so you avoid all sorts of the problems that shared memory brings, right? So you avoid race conditions, you avoid all sorts of the other. You don't need locking. And so that's all good. Basically, you just have these actors that work concurrently. And these messages, when they write the objects, they are placed in queues, right? So in chapter 12, if you remember, if you go back to your code in chapter 12, you had these sort of letterbox. So the object sent messages to another object, but then that message, because this was all single threaded, that message was processed immediately, right? Because there's just one thread going through all those objects anyway. When you go into the actor model where these objects are concurrent, then there is the situation that concurrent messages may come at the same object at the same time, right? So when you do that, if you don't want to lose those messages, then you have to hold them. You know, while the object processes one message, more messages may arrive. So you have to have some sort of a queue, right? So now the mailbox is actually a queue. There's a queue in there. And what the thread does is basically going through the queue, see if there are any messages in there, waiting for the message to arrive. And when the message arrives, it processes and comes back to check if there are more messages arrives, right? So the thread is on the loop. Each of these actor threads is on the loop, checking if there are messages, and if there are messages, then it processes it and so on. So the only thing that must be quote unquote thread safe, that you have to be careful in implementing the actor model, is the queues themselves need to be thread safe. So you cannot lose messages. So if two messages arrive at the same mailbox, you cannot lose them, right? So you cannot have race conditions at that point. So as long as you ensure that the queues are what's called thread safe, which means that no data is lost in the presence of concurrency, then the actor model is relatively simple, right? So basically, there's no shared memory because the data is copied around, and the queues are thread safe, so nothing is lost, and that's it. You basically just have concurrent actors, and they're all safe, thread safe. So here's how I do it in Python. Now let me backtrack a little bit. So the actor model in Erlang, which is a language that has been designed for this, gives you a lot of this by default, right? So you don't need to worry about, you know, thread safety in the queues, or you don't need to copy the data yourself when you send messages. Erlang does that all for you, right? If you try to implement the actor model in a language that does not have the actor model as the basis, then you need to be a little bit more careful. And so that's what I'm going to kind of talk about. So first, let me show you the example of you know, our exercise in in Python, how this looks like. So basically you have, what I modeled here is a abstract active object, okay, which is, I can do this by inheriting thread. I can do this with the object-oriented API very easily, right? By saying that these are subclasses of the thread class. I can also do this with the functional API, right? So if you're doing this in C++, then what you need to do is that, you know, C++ doesn't have the thread class, but you can create a thread in the constructor of this object, right? So that's the idea, and that's the thread that gets assigned to this object. So what is abstractly independent of what is it that these objects are doing. I have, you know, I modeled here an active object that has a constructor, and the constructor has a very important creation of the queue, right? So this is where the messages are going to be placed. Again, we're doing this in Java, in Python or Java, or whatever. It does not have the actor model as by default, right? So we have to model it ourselves. So here's the queue, and this queue in Python is an important important thing that you should know about the queue in Python is that this queue in Python is thread safe. Okay, where is it? Here, no, here. This is something that when you're going to implement this in another language, you know, you're going to instantiate a queue object in here. Make sure that you find the queue object that is thread safe. Okay, so keywords for Google search, the name of your language, thread safe queue. Right? Because, and I can tell you already, there's lots of queues in Java and C# and C++ that are not thread safe. Okay, and if you instantiate one of those that are not thread safe, then this is not going to work. You're going to witness race conditions in here. So make sure that you have a queue that is thread safe. In Python, that is the case here. And then it goes on a loop. So all of these active objects go on the same kind of loop, which is, you know, until it's stopped. It tries to get a message from a queue. And again, queue APIs vary, okay, across languages, and actually, typically there are many libraries. Yes, a mutex could work. Yes, so find out your, you know, whatever language you are working, whatever primitive thread primitives you have, figure out how to do a, yeah, blocking the queue will work in Java. Exactly. Do your research. Find out what's the right data structure that you want to use here in your particular language that you want to use. But let me tell you that all of these queues in all of the different programming languages are all slightly different. So you have to do your research. I'm showing you here how to do this in Python, but when you're going to do it in another language, you have to do your research. You just have to find out whether that queue that you want to use has the same properties as the one that I'm using here in Python or not. So let me tell you another property here. This queue in Python, not only it's thread safe, but it's a blocking queue. What that means is that if the queue is empty, the get operation blocks. Okay, so if this is not always kind of on a, this is not spinning. Okay, this is not always spinning. This is the thread. If the queue is empty, then it sits there. Okay, until something appears on the queue. And this is an important thing. Let me tell you why. Because there's many queues out there that in other languages that don't have blocking queues. Okay, don't have this blocking behavior. Okay, and so what they do is that if you do a get on the queue and there's nothing there, it gives you, I don't know, an exception or some, you know, returns -1 or something. Okay, but continues. It doesn't block. Okay, and so one kind of anti-pattern for what to do with these queues is that if you have a non-blocking queue, if your code is continually, you know, always spinning. Is it something here? Is it no? Is it something here? No. Is it something? This is going to be a very high CPU usage. It's really bad. Don't do that. Don't ever do a live spinning on a queue that doesn't block, because this is going to ruin the performance of your application. It's just going to basically it's occupying the CPU all the time, right? You basically will have one thread that is doing absolutely nothing, just destroying the environment, using energy for doing absolutely nothing. There's nothing in the queue. So make sure not to do that. If you are going to use a queue that is not blocking, you have to think a little bit careful how you're going to do it so that you are not on the spin all the time. Okay, there are techniques for doing that. For example, check if it's empty, then make the thread wait a little bit, a few milliseconds, for example. Okay, don't have the thread on the spin, because that's the absolute worst. That's like a high fever. That's like a person with fever. Okay, so having said that, Python, the get operation is blocking, so it stays here until there's something coming, and so when it gets out of here, it gets a message. Okay, and now it's the same thing as we did in chapter 12. It dispatches the message. All right, so that's basically all actors do this. The send operation, I just defined it here as just a regular function. You could also define it as a method of the active object. I don't really care. You have to have some send operation. So what does send mean in this world? It means putting a message in somebody's queue. That's what send means. Okay. So having defined these generic things, the active object and the send operation, then to model what we're going to do here, it's basically the same model as we used in chapter 12. So you have a data storage manager, which is an actor. You have a stop words manager, which is another actor. You have a words frequency manager, which is another actor. And some sort of a controller that's also an actor. So you have like 1, 2, 3, four active objects in this model that I did. So you basically have 4 threads. All right, so they're all concurrent. The internals are you will see are very similar to what you already did in chapter 12, actually virtually identical. There's just, the send operation is slightly different, but that's basically what it is. And so that's you have 4 different actors doing 4 different things, right? But they're all concurrent. Now, one thing that I should kind of point your attention to, which is a common mistake, that some of you are going to do a lot of. Maybe I shouldn't warn you, because it's kind of fun in a way that you bang your head on your keyboard with this error. But I will warn you. I'll be nice. I'll warn you. So one thing that is going on in here has to do with the sharing of the data when you send the message. Okay. So let me give you an example. For example, I don't know. For example, where is this guy, this data storage manager? So process words. All right, so process words. So this is a good example. It's a good spot to have bugs, concurrency bugs. So process words is going to split the file. It has a list of the words, and then for each of the words, it sends a message to the stop words manager. It sends a filter message to the stop words manager with it's called the payload. The data that's on this message is the word itself. Okay, so it sends a message that is modeled by a list in the case of Python, and the name of the message is filter, and the payload is word. Okay, the word that we are reading here. Okay. Now, be very careful on what kinds of things you're going to do to model this message. Okay, this is a message that I'm modeling as a list in Python because it's just convenient. Okay, if you're doing this in some other language like Java or C++ or C# or whatever, you may want, because creating lists is not as easy as this, you may want to have a class that models a message. Okay, so you have a class that models what the message is. It's going to have a string that's the, you know, the type of the message. It's going to have some sort of an object as the payload, right? And then be careful on how you manage those messages. And I'm going to tell you, I hope nobody falls into this, but I'm going to tell you already, especially those of you doing this in C++, okay, that you're going to do your own memory management. So one thing that I've seen several generations of students doing in C++ is that in this loop, at some point, you have to create a message object, right? So you create a message object to send it around. And as is typical of C++ programmers, your first reaction is always to optimize memory, right? So you want to always, that's a, you know, that's what C and C++ calls optimization always, right? So C++ programmers tend to be very scarce in terms of how many objects they are actually going to create. And so one very tempting thing to do is to just create one single message object, and every time in this iteration you just change the payload, right? So you update, you destructively update. You have, you know, an assignment. You have one single message object, and it might seem natural that all you do in here is to change the content of that message. That's all you do, right? It's something that a C++ programmer would kind of very tempting to do. You will, however, get into all sorts of problems if you do that, because now we're dealing with concurrency. And so as this thread over here is pushing words out in this message, there's another thread that is processing them. And it may not be processing them at the same velocity, at the same speed. It may be slower processing it, for example. So what's going to happen is that the producer of these words, this thread that's producing these words, if you just have one single message that you update every time, you're going to lose words. Okay, so I'm already warning you of one of the problems that you, especially C++. It may happen for those of you also doing this in Java and other object-oriented language. So be careful how you use memory. Okay, and that's a very important thing. And the spirit of the actor model here is that there is no shared memory. Okay, so when you send a message, it really should just go, a copy of the whole thing should go around. It should not ever, the sender of that message should never reuse that data again. Okay, it's like you send a message and the original message has to disappear. You're not supposed to hold on to it. Exactly, pass by value, not by reference, always. And so that's the kind of stuff that if you do it in Erlang, you don't even need to think, because that's what Erlang does. But if you do it in another language that's not Erlang, then you have to go to extra lengths to make sure that things are not passed by reference. Okay. Okay. Any questions about this? All right, so let me go. Queues, I think I mentioned this. They all, one way or another, provide operations for put. Sometimes they're called enqueue, sometimes they're called send, but it's basically the operation of putting something in the queue, and then have another operation of getting it or taking it out. You know, dequeue, receive. The operations must be thread safe, and make sure that you also understand whether the get is blocking or not, and what to do if it's not blocking. So those are all the interesting things that you, additionally to whether the queue is FIFO or LIFO or whatever, you have to understand the concurrent behavior of those data structures that you're going to use. Okay, very important. And you know, in this particular case, we're dealing with a queue, but there's a whole series of all other data structures that usually come in standard libraries that is the same thing, that you have to know. If you're dealing with a concurrent program, you have to know if those data structures are thread safe or not, and what is their model when you take things from them or put things from them. Do they block? Do they don't block? So those are all additional things that you need to think about when concurrency is brought into the picture. Some examples of thread-safe queues, there are others. So Java, the array blocking queue is one, but there's others. Concurrent queue in C#, C++. Also, if you use Boost, there's a message queue that is safe, as far as I know. So other languages, search for it, okay? Or do it yourself. You can also do a queue. All right, so the actor model, so how does it constrain the threads? It's constrained by associating certain objects with threads, okay? So basically now threads are bound to specific objects of your application, okay? So there's no creation of threads somewhere in the middle of this. No, there's not, no. There's only certain objects that you design a priori, you know which of these objects are actors, okay? And that's it. And so the using the message queues in each actor, right? So there is no sharing of, you know, behind the scenes or back doors or whatever. No, everything that enters the actor enters through the queue, not to some back door. And also these threads are always on a loop. They don't go out to other actors, right? The threads are always on a loop. And what they do is check the queue, take a message, process it, right? And this processing is an internal thing in the actor. It only accesses data that is available to the actor. Okay, highlight the differences between the actor model and channel model, like the one using Golang and C#. The channel model. So the channel model, that's a good question. So the channels are basically queues. Okay, so they are queues that exist independent of the objects. And that goes more into the next thing that I'm going to talk about, okay? So it goes a little bit into the data spaces. So let me move on. So tuple spaces or data space, whatever you want to call it, are they are good for when there are concurrent threads, but where certain threads produce the data and certain threads consume the data, right? And so this is where this idea of a channel starts coming into, because they're communicating data, right? And there are these shared data structures that can be, you know, queues or lists or trees, something, you know, that holds on to the data that is going to be shared between the producers and consumers. And these ones must be thread safe. Okay, these things must be, you cannot lose data that is placed on these shared data spaces. What producers do is that they add the items and they move on. So it's an asynchronous deposit. So they add the items there and just continue do whatever they're doing. The consumers take the items and process them, right? So this is sort of similar to the previous model, but where the queues are outside of the objects, and may not be queues at all. It may be some other data structure, you know, whatever, trees or whatever is necessary to do this processing. Okay, so it's sort of like this. There's these threads. They are concurrent. Each of these is a concurrent thread, but now they're sharing the space, and some of them are putting things into the space. Some of them are taking things from the space. So let me show you how this looks like in Python. All right, so the way I could have modeled this in many ways, but I modeled this in two channels, if you want to call it, or data spaces. So two separate data spaces. One of them is the word space, and the other is the frequency space. Okay, I just did two just for fun. So the word space is supposed to have producers of words that put words into this space, and consumers of words that take words from this space and process them. Okay, and producers and consumers are concurrent, and there can be many producers and there can be many consumers. All right. And then just to add a little bit fun, I have another space, another channel, if you want to call it like that, that each of these consumers of the words do the processing, their own local processing, and then their local results at the end get placed in this shared frequency space, right? They put frequency, basically dictionaries, maps into this space. And then there's other consumers of these temporary dictionaries that merge them all together at the end. So that's the idea. So I have these two, the way that you need to sort of think about it, there are producers of words that put the words into a shared space. There's consumers of these words that take the words out and process them, and many of them in parallel. Okay? So each one is going to have its own local results. And as they finish processing, they put their local results into this frequency space. And then there's another consumer of these frequencies that takes them out and merges them all together for the final result. Okay, so this is the channel model, basically. Okay, these data spaces are the channels between these producers and consumers. So so I'm creating these two spaces. And then here's the worker function that consumes word. Let me start from the bottom, actually. The bottom is, right, the main method actually starts here. So the main thread is just one. It's going to be the producer of words. So in general, there could be many producers, but in this case, I'm just, it's just one file. I'm just putting one thread producing old words. So basically, it's splitting the file, and every single word is putting it on the shared space for the words. Okay, that's what the main method does. And then it creates the workers. I could have done this slightly different. I could have created the workers first. I should have created the workers first, because then they could start working immediately as this guy starts putting words in there. You feel free to do that. It's more in style, right? Because typically you have the producers and consumers working at the same time. The way that I wrote this, the space is populated first, and then only then you create the consumers, and then the consumers start working in parallel. Little details. So you create the workers, and there's an array of workers. Here I'm using the functional API for creating threads of Python. Okay, because we don't need objects here; it's just a function, and the function is process words. And then I start them all. So let's do what this function does. It has its local word frequency dictionary, and it gets something from the queue. Bear in mind that there's a timeout here. I'll explain what this means. So it gets a word from the queue, and then it does the processing, right? So it does the processing. It puts it in its local frequency dictionary, and then at the end, when there are no more words, it puts that dictionary in the shared channel for dictionaries. Okay, that's all it does. Now, little details in here. I told you just previously that the get in Python is blocking. Okay, so given that it's blocking, what would happen at the very end, okay, when there are no more words, it would come back to here, and all the threads would block. They would not be able to continue, right? So what I have here is a little timeout, and this again, the particular API of Python. You guys have to figure out how to do it in the language that you're doing it. So that this thread doesn't block at the end. So it needs to unblock, and I'm forcing it to unblock with a timeout of 1 second. So if no word shows up in the queue in the data space for 1 second, then this times out, and with an exception, queue empty. Okay, and then I break. And then I can finally put this frequency space, the word frequencies in the frequency space. Okay. All right. So that's what 5 workers do concurrently. While the main thread just waits for them, and then it waits for it waits for the workers to finish, and then it's actually the main thread, just one, that's going to merge all the local dictionaries. So the main thread is also just a one single thread consumer of all the local dictionaries of the threads. Okay, so there it is. It goes to the frequency space and gets all of the the partial dictionaries and merges them and then prints at the end. Okay. Questions about this? So let me just tell you, this is a very basic concurrency model, super useful. You see it in many situations. For example, let me give you an example where this is used. Web servers, for example, or servers of any kind. So typically, yes, workers here is an array of threads, exactly. And basically it can be your own array of threads, or you can use all of these languages that have some sort of a thread pool that you can also use, that's already there for you to use if you want. But it's an array of threads. So this model, for example, when you have servers, network servers, typically you have a lower level listener, the socket listener that's listening to the socket on a loop, right? And when some message comes, some request comes, rather than this listener thread processing the request itself, in multi-threaded servers, the way that this is done is typically the lower level thread that's listening, the listener thread. The only thing that it does is when the message arrives, it puts it on a queue. That's all. That's all it does. It gets, it listens on the network, something arrives, dumps that something on the queue. And then you have a thread pool. You have some pool of threads, okay, some workers, called worker threads that do exactly this. Look if the queue has something there and take things from the queue and process them. That are the request handlers of some sort. And when you have a multi-threaded server, then this the request handlers can be processed concurrently, right? So you can have many threads when you have a lot of clients at the same time. You can have many threads processing them concurrently. So how many workers should we have? I have 5 workers here, so you should do the same. Okay, just do the same. In general, how many workers you should have depends a lot on lots of things, on the context of your application, how many clients you have, how fast the data is produced, how many CPUs you have. So it depends on many things what the right number of threads is. And sometimes there's even some more sophisticated frameworks that adapt the size of the thread pool depending on what's going on. Okay. All right, so now let me go to the next one. So actually just to wrap it up, the tuple space model can be functional or OP style. What I showed you is functional style, but you can very easily have these workers also being active objects, basically. Right? You have these model the threads as objects. And again, the best fit is for data processing parallelization. So when you have some producer of data and then you have the processing of the data can be parallelized, and you have you put the data in this queue, the shared space, and then you have the consumers processing the data. Concurrency is constrained by having a shared thread-safe collections of items. So it's important that these channels, these data spaces are thread-safe. That's the only thing that you need to ensure. Okay, that's the only locks that should ever happen if you need to add locks is on these queues or whatever. The data structures that are shared need to be thread-safe. And it's also constrained by having the role of producers and consumers of items in this collection. So typically in this model, you don't have threads that are both consumers and producers. Okay, you have threads that are producers and you have threads that are consumers, but they don't do both things at the same time. And basically there's no further communication between the threaded code. Nothing. The only thing is that there is this data space, okay? And some threads put data in there, and other threads take data from there. That's all. And again, you need to remember to be careful with passing things by reference if you're doing this in an object-oriented language that does not support these channels by default. Okay, the threat and the danger of putting references in these queues is always there, especially. It may be again. You may kind of relax this constraint a little bit in this particular model, because if you know, and okay, if you are absolutely sure that the producer is never going to access that object ever again, okay, if you are absolutely sure, then you can pass an object reference to the consumers, okay. But you do it at your own risk. That's basically, always the thing here with these models. So let me talk about MapReduce. So MapReduce model is a good one for like big data situations when the problem at hand can be data parallelized. And it's one situation, one good example of MapReduce application is one where you have the data is continuously coming at you. It doesn't just stop. It's just continuous coming at you. So you have a stream of data. I'm not going to talk about streams today yet, but it's also definitely a characteristic of MapReduce. But in any case, what I'm going to focus in here in the exercise is the idea that you can split the data. Okay, the data that you're going to process is somehow splittable in chunks. Okay, and now you can have each chunk be processed in parallel by several worker threads. Okay, and again they produce partial results. They don't produce the result. Each one of these worker threads does not have the complete result. You still need to have another phase, which is the reduce phase, which we saw a little bit in the previous example too. But so the reduce phase, you kind of merge these things, these partial results together, and you create, the final result. So the interesting thing is that by of the camera. Anyway, so let me talk about continue to talk about the MapReduce. So there's interesting things about seeing the problem as one where the front ends can be parallelized, and the back end, there's interesting things about you can do when you're going to merge the data on the back end that also can have interesting options. Okay, so let me explain what that means. So I have two versions of MapReduce in the book, and they are almost the same, but not quite. So the first one is the simplest one. It's like the straightforward MapReduce, in which we're dealing just with one file here. Typically, MapReduce is used when you have thousands of files, and now you're going to process a big chunk of files at the same time. So in order for me to emulate the input data being sharded, I read the file, and then I split the file in the chunks of, I think it's 200 lines or something like that, if I remember correctly, something like that. So I have chunks of 200 lines, right? And those are the input data being partitioned. And so what I'm going to do now, the concept of MapReduce comes from Lisp. Again, it's a functional idea that you have a function in the library, that's the map function, that takes a list of chunks and a function, okay, and applies the given function to each of the chunks of the list. Okay, again, this is an kind of API that has been in Lisp since the 1960s. All right. So the map is a higher order function that takes two arguments. The first argument is a function, and the second argument is a list of data. Okay? And so what map is going to do is apply the function to the list, each of the elements of that list. And the interesting thing about this is that because it's so abstract, it can do this in many different ways. It can do it in sequence, but it can also do it in parallel, right? So now it's up to the implementers of the map function, which are not us. The implementers of the map function can have a lot of options for how to actually implement the mapping of a function to a list of data. In particular, they can do it concurrently. They can, send it over the network. There's lots of things that can be done. So that's the map, right? And so at the end of the map function, you get a list of partial results, right? So each of these workers got a result, right? And so you now need to merge it. And that merging is done by a reduce function, a concept of reduction of the data, which is, again, a function that takes, it's a higher order function that takes a function and a list of partial results. And then it's going to merge these partial results 2 by 2. It's like Pac-Man. Okay, so it starts with the first one, it merges the first one with the second, and then the second one, and then that thing merges with the third one, and then that thing merges with the fourth one. So I like to think of this as a Pac-Man function. All right, and then you finally have the results at the end. So if you look into my implementation, the simple implementation of MapReduce. So here's the main function. So the main function, I partition the data, yes, in 200. So I read the file and then partition the file in chunks of 200 lines. Okay. And for each of those, so the partition is a function that returns a list of data. Okay. Of groups of lines from the file, from the original file. And then what I'm giving that to the split words function. Okay, so I'm mapping the split words to each of those inputs. So the split words does what it says, takes a string and returns a list of pairs. Now this is the interesting thing. MapReduce has this interesting minimalistic approach in that the mapper function, in this case split words, is supposed to be as dumb as possible. Okay, so the mapper function does what it absolutely needs, the minimum absolute work that it needs to do in order to be able to do its job. So in this case, it's not doing any fancy thing at all. Okay, this is as brain dead as you can imagine. The only thing that it does is that it takes a string, okay, and returns a list of pairs saying, I saw this word. Okay, so for example, if you have, the rabbit jumped. So you say, you generate the with not one, okay, a pair, the one, rabbit one, jumped one. So those are the words that it sees. It basically literally splits the words. It doesn't try to do anything fancy like counting the words that are the same, right? Already in that, it doesn't even do that. Okay, so it just produces these pairs. I saw this word, I saw this word, I saw that word. That's all it produces. It sends it down the chain. Okay. So what the reduce function is going to do is that it's going to get those splits, right? Those pairs, and it's going to count the words. This is the one that actually going to count. The counting is going to be done on the reduction function. So the count words takes two lists of pairs of the form like this, okay? Pairs of words. Word counts, that's always, the count is always on. and returns a list of pairs that actually have the actual count, right? Word 1, I saw it this time. Word 2, I saw it this time, okay? Where the frequency is the sum of all the reported occurrences. So this is how it does it, right? So at the end, you have a dictionary that has all the word counts, right? So again, the interesting thing is that the logic of counting is not done on the front end; it's done on the back end. Right? So there's a front end is the mappers, and there's the back end is the reducers, and the logic is typically done on the back end, not on the front end. The front end is very dumb. It just really just does as lightweight as possible and splits things basically. It just splits things and routes things. So that's the basic MapReduce. But it gets more interesting than this, okay? It gets more interesting because if we do MapReduce like this, we can parallelize the front end with many mappers, right? As we did here. So we partition. Actually, let me tell you one thing. The way that I'm doing this in Python is actually not concurrent because the map function in Python doesn't implement things concurrently, as far as I know. Okay. So Python has a map function, but it does not do concurrent implementation, right? It could, but it doesn't. So you should probably find out in whatever language you use whether the map function is concurrent or not, and leave a comment in your code about it. But in any case, whether it's concurrent or not, it could be concurrent. Obviously, it could be concurrent. But what we have here, the reduced function, cannot be concurrent, right? So now we have a bunch of partial results coming from the front end, and the backend job is merging them, pairwise, okay? And that is basically bangs a bottleneck. It's just serializing. Everything now needs to go through this reducer function. It's just one function that is executing. All right. And so this is not necessarily what we want. We can do a little better to also have parallelism on the back end. So let me show you another way of doing MapReduce. And this is more true to how Google popularized MapReduce. So this is the same exact thing, almost. It has a little bit in the middle. Here's something in the middle. So the main function is the same thing. Split the front end data, split the words. The what comes out of split words is exactly the same thing. So basically, these pairs, word one, another word one, another word one. But then before we reduce, okay, before we feed this to the reducer, we do a regrouping of the splits, okay? So this regrouping is an interesting thing that we can do in this architecture. So what's going on in this regrouping? So let me just tell you the higher level picture. The interesting thing, we're dealing in this particular data, which is words, okay? We're dealing with words, textual data. So textual data is, uses letters of the alphabet, all right? So at the end, we want to have a dictionary of how many times did we see the word Elizabeth, how many times did we see the word Darcy, things like that, right? So that's what we want at the end. But we can actually end up with not just one single dictionary at the end, but we can end up with many dictionaries at the end, which is logically just one. That's the important thing. How? By charting on the letters of the alphabet. So we can say we have one dictionary that holds all the words from A to C. Another dictionary that holds all the words from D to H or whatever. And so we can partition the target space in ways that make sense for that particular data. Textual data is very easy to do. If it's other numerical data, you can also do some sort of a partition on numerical data. Whatever data you have, if it can be partitioned like this, that's the idea. So we can end up now with several receiving dictionaries, but the important thing is that the word Elizabeth is only going to be in one. It's not going to be split in many dictionaries. Otherwise, it would be hard to find out when we query, how many counts of Elizabeth. Then we would have to query many dictionaries. We don't want that. We want to have just one place where we're going to query the word Elizabeth. And so what this regrouping is doing, I think what I'm doing here is actually not groups of letters. I'm doing a dictionary per word. It's a little crazy, okay? So is it per word or per letter of the alphabet? Let's see what it's doing. No, it's per word. So there you go. So basically takes a list of pairs and returns a dictionary mapping each unique word to the corresponding list of pairs. All right. So word 1, these are all the pairs that it has. Word 2, so it's basically like I have a receiving dictionary at the end that is going to have a one pair word. Now, in your exercise, I'm asking you to do something a little smarter than this. I'm actually asking you to do the right, what MapReduce does. The typical MapReduce is just partitioning the alphabet. Okay, so rather than having a one dictionary, one little thing per single word, you have ranges of the alphabet. Okay, so that's but basically what is going on in here is that there is I call it regrouping here, but in the real MapReduce architectures, because these are streaming architectures, this regrouping is actually a routing operation. Basically, let me see if I have those slides here. I don't have those slides. But basically, in a real architecture of MapReduce at the data center level, you have a series of servers that are the front-end mappers. Okay? So you have these series of servers that are the front-end mappers that are all processing similar data as the input data as it comes. And then you have a series of servers on the back end that are somehow partition the output data in ways that make sense for that particular data. So if it's textual, you can do it alphabetically, or if it's numerical, you can do it by ranges, whatever. And then in the middle between the front end mappers and the reducers at the end, there's sort of a routing, which is if it's textual data, this particular mapper, if it's dealing with the word starting with C, then it routes to that particular mapper on the reducer on the back end that takes care of the words with C, right? So that's sort of a routing rather than a regrouping, to make sense when you're dealing with strings. Okay, so let me go here to your exercises. No, here to the exercise and just show you the regrouping here. So the regrouping, as I said, takes a list of lists like this and returns a dictionary mapping each unique word to the corresponding list of pairs, so like this. And then the reducer is sort of more or less trivial. It's the count words. It just it can do it in basically one. It can reduce one in parallel. Basically, can you reduce in parallel? You can have many reducers, one per word in this case, right? So what I'm asking you to do for the homework is week 6. All right, so week 6. Right, so chapter 32, exercise 32, but with 32.3 grouping. So the point 32.3 is, so reorganizing the pairs on the pair word basis might be a bit too much parallelism. So change the program so that the regroup function reorganizes the words alphabetically to 5 groups: A to E, F to J, K to O, P to T, and U to Z. Okay. So then the counting function needs to, it's not exactly the one that I have. You need to change it to. Okay, so what is MapReduce? Just to wrap it up. So MapReduce is a concurrency model that's constrained by having worker threads work on mutually exclusive chunks of data. There's no communication at all between these threads. There's only producing, the front end produces data that it routes to the, down the stream to the backend reducers. And then something is produced at the end, which can be just physically just one result, or logically one result that is physically split among several reducers too. So that's both valid concepts of MapReduce. As I said, I want to say this again. In the exercise that I have here and the exercise that I'm asking you to do, I don't have the important part of MapReduce, which is the streaming. Okay, the streaming of data. I will talk about streaming next week when we talk about those kinds of styles. But so I wanted to kind of isolate the concurrency and the model of splitting the input and processing the input concurrently and then reducing partial results. That's a concept right there. That's independent of how, whether it's streamed or not. Okay, so MapReduce is a model where you process the input in parallel, you produce partial results from each of the parallel processing, and then you have to reduce those parallel results in some way. Okay, you have to merge them together. All right, so and we're running out of time, so I guess I'm not going to go to the next week's lecture after all.